aperiodic, and non-periodic. Redirect here. For other uses, see aperiodic. In mathematics, a periodic function is a function that repeats its values in regular intervals or periods. The most important examples are the trigonometric functions, which repeat over intervals of 2 pi radians. Periodic functions are used throughout science to describe oscillations, waves, and other phenomena that exhibit periodicity. Any function which is not periodic is called aperiodic. Definition: a function f is said to be periodic with period p if we have for all values of x in the domain. If there exists a least positive constant p with this property, it is called the fundamental period. A function with period p will repeat on intervals of length p, and these intervals are referred to as periods. Geometrically, a periodic function can be defined as a function whose graph exhibits translational symmetry. Specifically, a function f is periodic with period p if a graph of f is invariant under translation in the x direction by a distance of p. This definition of periodic can be extended to other geometric shapes and patterns, such as periodic tessellations of the plane. A function that is not periodic is called aperiodic. Examples: for example, the sine function is periodic with period 2 pi, since for all values of x, this function repeats on intervals of length 2 pi. Everyday examples are seen when the variable is time. For instance, the hands of a clock or the phases of the moon show periodic behavior. Periodic motion is motion in which the position of the system are expressible as periodic functions, all with the same period. For a function on the real numbers or on the integers, that means that the entire graph can be formed from copies of one particular portion, repeated at regular intervals. A simple example of a periodic function is the function f that gives the fractional part of its argument. Its period is 1. In particular, f equals 0.5. The graph of the function f is the sawtooth wave. The trigonometric functions sine and cosine are common periodic functions, with period 2 pi. The subject of Fourier series investigates the idea that an arbitrary periodic function is a sum of trigonometric functions with matching periods. According to the definition above, some exotic functions, for example the Dirichlet function, are also periodic. In the case of the Dirichlet function, any non-zero rational number is a period. Properties: if a function f is periodic with period p, then for all x in the domain of f and all integers n, f equals f. If f is a function with period p, then f, where a is a positive constant, is periodic with period p. A, for example, f equals 6 has period 2 pi, therefore sin will have period 2 pi. 5. Double periodic functions. A function whose domain is the complex numbers can have two incommensurate periods without being constant. The elliptic functions are such functions. Complex example. Using complex variables we have the common period function. As you can see, since the cosine and sine functions are periodic, and the complex exponential above is made up of cosine, sine waves, then the above has the following property. If L is the period of the function, then generalizations. Antiperiodic functions. One common generalization of periodic functions is that of antiperiodic functions. This is a function f such that f equals minus f for all x. For example, the sine or cosine function is pi antiperiodic in 2 pi periodic block periodic functions. A further generalization appears in the context of Bloch waves and Floquet theory, which govern the solution of various periodic differential equations. In this context, the solution is typically a function of the form, where k is a real or complex number. Functions of this form are sometimes called Bloch periodic in this context. A periodic function is the special case k equals 0, and an antiperiodic function is the special case k equals pi p. Quotient spaces as domain in signal processing. You encounter the problem that Fourier series represent periodic functions and that Fourier series satisfy convolution theorems. But periodic functions cannot be convolved with the usual definition, since the involved integrals diverge. A possible way out is to define a periodic function on a bounded but periodic domain. To this end you can use the notion of a quotient space. That is, each element in is an equivalence class of real numbers that share the same fractional part. Thus a function like is a representation of a one-periodic function.